There's something unsettling about looking up at the night sky, not just because of its vastness, but because of the secrets it refuses to give up. Take this, for example. Right now, the universe isn't just expanding, it's accelerating, speeding up as if propelled by some invisible hand. Scientists call it dark energy, a mysterious force making up nearly 70% of the cosmos, and yet we have no idea what it actually is. This isn't some small gap in our knowledge, it's a yawning chasm, a cosmic shrug from the universe itself. But here's the thing, dark energy is just one piece of a much larger puzzle. Beyond the planets, the stars, even the galaxies, there are forces at work that defy our understanding, bending reality in ways we're only beginning to grasp. Think about gravity for a moment. You feel it every day. It keeps your feet on the ground, your coffee in the cup. But what if I told you gravity might not even be a force at all? Some theories suggest it's simply the curvature of space-time, a wrinkle in the fabric of the cosmos. And then there's dark matter, an invisible scaffolding that holds galaxies together, outweighing visible matter 5-1. We can't see it, we can't touch it, yet without it, the universe as we know it would fly apart. These aren't just abstract ideas, they're the hidden threads weaving the tapestry of existence itself, and they're everywhere, shaping everything from the birth of stars to the fate of the cosmos. That's what this journey is about, the 30 unseen forces quietly steering the universe, from the quantum weirdness that governs atoms to the colossal mysteries lurking in deep space. Some of these forces are so strange they sound like science fiction, yet they're as real as the ground beneath you. Others are so subtle we've only just detected them, like ripples in space-time from colliding black holes billions of light-years away. But here's the most thrilling part. Every one of these forces opens a door to new questions, new possibilities, new ways of seeing the universe and our place within it. So let's pull back the curtain together, because what you're about to discover might just change how you see everything. Of all the mysteries in the cosmos, dark energy might be the most baffling. Picture this, the universe isn't just growing, it's stretching faster every second, like a runaway balloon inflating itself against all logic. We first caught hints of it in the late 1990s, when astronomers studying distant supernova noticed something bizarre. These exploding stars billions of light-years away were fainter than they should have been, as if space itself had stretched during their light's journey to us. The only explanation, some invisible force was pushing the universe apart, and not just steadily, it was accelerating. Now here's where it gets even stranger. Einstein actually predicted something like this a century ago with his cosmological constant, a mathematical fudge factor he later called his biggest blunder. Turns out he might have been right all along. Dark energy behaves eerily like that constant, a sort of anti-gravity woven into the fabric of empty space itself. And it's not some minor player, it makes up 68% of the universe's total energy. To put that in perspective, everything we can see, stars, planets, galaxies, accounts for less than 5%. The rest, that's dark matter, but dark energy, it's the dominant force, the silent puppeteer shaping the fate of everything. What does that mean for the cosmos? If this acceleration keeps up, galaxies will eventually rush apart so fast their light will never reach us. The universe could end not with a bang, but with a cold, lonely fade into darkness. Yet for all its power, we still don't know what dark energy actually is. Is it a property of space, a new kind of particle, or something beyond our current physics? Every telescope, every experiment brings us closer to the answer, but for now, it remains one of the greatest unsolved riddles in science, a reminder of how much we still have to learn about the universe's hidden blueprint. But here's the twist, dark energy might not be as constant as we think. Some scientists suspect it could change over time, growing stronger or weaker, reshaping the universe in ways we can't yet predict. This idea, known as quintessence, suggests dark energy isn't just a static feature of space but a dynamic field. almost like an invisible fluid that ebbs and flows. Imagine turning a dial that controls the expansion of the cosmos itself, except we don't know who's turning it or why. Then there's the competing theory, vacuum energy. Picture empty space not as true nothingness, but as a seething quantum foam, particles flickering in and out of existence. According to this view, dark energy is the cumulative hum of these quantum fluctuations, a relentless pressure pushing space apart. Einstein's cosmological constant fits neatly here, but there's a catch. When physicists calculate how strong this energy should be, the numbers are outrageously wrong, off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It's the largest discrepancy ever between theory and observation, a glaring sign that something fundamental is missing from our understanding. This is where missions like Euclid come in. Launching soon, this space telescope will map the cosmos in unprecedented detail, measuring how galaxies cluster and how light bends over billions of years. By tracking the universe's expansion with razor precision, Euclid could reveal whether dark energy is truly constant or if it's shifting, a clue that might crack open the door to new physics. Because right now we're stuck with a paradox. The force driving the universe's fate is also the one we understand the least. Whether it's quintessence, vacuum energy, or something entirely stranger, solving this riddle won't just rewrite textbooks, it could redefine reality itself. If dark energy is the universe's mysterious accelerator, dark matter is its invisible glue. While stars and planets make up less than 5% of the cosmos, dark matter outweighs everything we can see by a factor of 5, yet it refuses to interact with light, leaving us to detect its presence only through the ghostly fingerprints it leaves behind. The first clue came in the 1930s when astronomer Fritz Zwicky noticed something bizarre about the Coma galaxy cluster. The galaxies were moving so fast they should have flung themselves apart, yet something unseen, was holding them together with an iron grip. He called it Dunkelmaterei, dark matter, a term that would haunt physics for decades. Fast forward to the 1970s, and Vera Rubin's observations of spiral galaxies deepened the mystery. The stars at the edges of these galaxies were orbiting just as fast as those near the center, defying Newton's laws. Imagine a vinyl record spinning on a turntable. The outer edge moves faster than the center. But in galaxies, the outer stars whip around at the same speed, as if some hidden hand was tugging them along. The only explanation, an enormous halo of invisible matter, far larger than the visible galaxy itself, must be warping the rules of motion. But how do you study something you can't see? Enter gravitational lensing, one of Einstein's strangest predictions. When light from a distant galaxy passes near a massive object, like a galaxy cluster, its path bends, distorting the image like a funhouse mirror. But here's the kicker. The amount of bending we observe often requires far more mass than the visible stars and gas can account for that extra mass. Dark matter again, sculpting space-time itself. Telescopes like Hubble have captured these cosmic mirages, revealing intricate rings and stretched galaxies where dark matter's grip is strongest. And then there's the cosmic microwave background, the faint afterglow of the Big Bang. Tiny temperature fluctuations in this ancient light act like a fingerprint for the early universe's structure. The patterns match a universe where dark matter makes up 27% of everything, acting as the scaffolding for galaxies to form. Without it, the universe would be a featureless void, no stars, no planets, no us. So what is this shadowy substance? Theories range from WIMP, weakly interacting massive particles, to axions, hypothetical particles lighter than an electron. Some even suggest dark matter might be primordial black holes, remnants of the universe's chaotic infancy. But after decades of searching, from deep underground detectors to particle colliders, we've found nothing conclusive. It's as if the universe is teasing us, dangling clues just out of reach. Yet every failed detection teaches us something new. Maybe dark matter isn't a single particle but a family of them, or perhaps it interacts in ways we haven't even imagined. Upcoming experiments like the Vera-C, Rubin Observatory's decade-long sky survey could finally crack the case, mapping dark matter's distribution with unprecedented precision. One thing's certain, solving this riddle won't just fill a gap in our knowledge, it could rewrite the laws of physics. Because right now, we're living in a universe where the majority of matter is utterly invisible, shaping everything around us while remaining just beyond our grasp. Among the leading candidates for dark matter's identity, one stands out as both promising and frustratingly elusive: weakly interacting massive particles, or WIMP. Picture these as cosmic phantoms, particles with enough mass to tug on galaxies through gravity, yet so indifferent to ordinary matter that they pass through planets like ghosts through walls. The theory behind them is elegant. If dark matter is made of WIMP, they'd belong to a class of particles predicted by supersymmetry, a framework extending the standard model of physics. These particles would have formed in the searing heat of the early universe, then lingered as relics, their sheer abundance explaining why they outweigh visible matter 5-to-1 today. But how do you catch something that barely interacts with anything? Enter experiments like Xenon 1T, a vat of ultra-pure liquid xenon buried deep beneath Italy's Gran Sasso mountain to shield it from cosmic rays. The idea is simple yet audacious. If a WIMP drifts through the detector, it might bump into a xenon nucleus, creating a flash of light and a trail of electrons. Scientists have spent years refining these detectors, making them so sensitive they could spot a single WIMP collision among billions of passing particles. And yet, despite their precision, the detectors remain silent. No flashes, no trails, just the eerie quiet of a universe keeping its secrets. That silence has pushed physicists to consider alternatives, like axions, particles so lightweight they were first proposed to solve a puzzle in quantum physics, not dark matter. Imagine them as cosmic wisps, billions of times lighter than electrons, drifting through space like an intangible mist. Unlike WIMP, axions wouldn't collide with matter at all. Instead, they'd reveal themselves through a bizarre quantum effect. In the presence of a strong magnetic field, they might transform into photons, creating a faint radio signal. Experiments like ADMS hunt for this whisper-thin signal, tuning their detectors like radios scanning for a station just out of reach. The challenge with both WIMP and axions is scale. A WIMP might interact once in a ton of xenon over a year, while an axion signal could be drowned out by the hum of the cosmos itself. This is why newer detectors like Xeno NNT and LZ use ever larger volumes of xenon, while axion hunts deploy ever stronger magnets. But the longer these searches come up empty, the more physicists wonder, are we looking for the right thing, or is dark matter something stranger still? Some theories now propose entire dark sectors, hidden families of particles interacting through forces we've never seen, a shadow universe paralleling our own. What's striking isn't just the mystery of dark matter's identity, it's how profoundly its detection would reshape physics. Finding WIMP could validate supersymmetry, a theory that elegantly fills gaps in the standard model. Axions might explain not just dark matter, but why the universe has so little antimatter. And if dark matter belongs to a hidden sector, that could mean undiscovered forces, particles, even dimensions lurking just beyond our reach. Every experiment, every null result, inches us closer to answers or to rewriting the questions entirely. Because in the hunt for dark matter, the greatest discovery might not be finding what we expect, but realizing how much we've yet to imagine. If you could peer into the quantum realm, you'd discover something astonishing. There's no such thing as empty space. Even in the deepest void between galaxies, the fabric of reality crackles with energy, a seething ocean of virtual particles flickering into existence and vanishing again in less than the blink of an eye. This is the quantum vacuum, and far from being passive nothingness, it's one of the most dynamic forces shaping our universe. Take the Casimir effect, where two uncharged metal plates placed micrometers apart in a vacuum inexplicably move toward each other. Why, between the plates, only certain wavelengths of virtual particles can exist, while outside, all wavelengths are possible. This creates a pressure imbalance, a literal force from nothing pushing the plates together. It's as if the universe is a restless painter, dabbing invisible brushstrokes of energy everywhere, even where we perceive emptiness. Now imagine this quantum froth magnified to cosmic scales. Some theories suggest these microscopic fluctuations could have been the seeds for the largest structures in existence. During the Big Bang, quantum jitters in the vacuum might have stretched to astronomical sizes, forming slight density variations in the early universe. Over billions of years, gravity amplified those tiny ripples into the vast web of galaxies we see today. In essence, the universe's grand architecture, threads of galaxies spanning billions of light years, could trace back to fluctuations smaller than an atom. But here's where it gets wilder. Quantum vacuum energy might also be fueling dark energy, that mysterious force accelerating the universe's expansion. Calculations suggest the vacuum should contain staggering energy, enough to tear atoms apart instantly. Yet we observe only a faint whisper of that power. This discrepancy, known as the cosmological constant problem, is one of physics' greatest puzzles. Is our math wrong? Are we missing hidden dimensions or undiscovered symmetries? Or does the vacuum somehow cancel out most of its own energy, leaving just enough to nudge galaxies apart? The implications are staggering. If quantum fluctuations truly sculpted the cosmos, then everything from galaxy clusters to the voids between them might owe their existence to this ghostly quantum dance. Even now, particles wink in and out beneath your feet, around your hands, everywhere. An invisible symphony of creation and annihilation that might hold the keys to understanding reality itself. And while we're only beginning to grasp its role, one thing's clear: the universe is anything but empty. It's a living, breathing quantum sea, and we're just beginning to learn its tides. Picture the universe in its first moments, a trillionth of a second old. When something extraordinary happened, space didn't just expand, it erupted, stretching faster than the speed of light itself, swelling from smaller than an atom to the size of a grapefruit in less time than it takes light to cross a single proton. This wasn't just growth, it was cosmic inflation, a violent surge that ironed out the wrinkles of the newborn cosmos, leaving behind a universe so smooth and flat that its echo still lingers in the sky today. The evidence for this explosive beginning is etched into the oldest light we can see, the cosmic microwave background, that faint afterglow of the Big Bang. When satellites like Planck mapped this radiation with exquisite precision, they found whisper-thin temperature variations, hot and cold spots no larger than 100,000th of a degree. These tiny fluctuations are cosmic fingerprints, the stretched-out remnants of quantum jitters from inflation's final moments. Think of it like blowing up a balloon with microscopic dots drawn on it. The dots grow fainter and more evenly spaced as the balloon inflates, mirroring how inflation smoothed the universe's initial chaos into the subtle patterns we now observe. But inflation's implications go far beyond just explaining the universe's smoothness. It also solves the horizon problem, a puzzle that baffled cosmologists for decades. When we look at opposite ends of the observable universe, those regions have the same temperature, meaning they were once in thermal contact. Yet without inflation, they'd have never had time to exchange heat. They'd be like two strangers on opposite sides of the planet wearing identical outfits by pure coincidence. Inflation fixes this by revealing those regions were once neighbors, stretched apart in an eye blink by the universe's hyper-fast expansion. Now, here's where things get truly mind-bending. Some models of inflation suggest it never truly stopped, that our universe is just one bubble in a frothing multiverse, where countless other bubbles inflate endlessly, each with their own laws of physics. In this view, the Big Bang wasn't a unique event but a local one, our cosmic neighborhood in an infinite ocean of universes. String theory even proposes these bubbles could collide, leaving scars in the CMB, though searches for such anomalies have so far come up empty. The most staggering part, if inflation is real, then everything we see, every galaxy, every star, is just quantum noise amplified to cosmic scales. Those infinitesimal fluctuations in the early universe's energy field became the seeds for galaxies, planets, and ultimately us. It's as if the universe took a quantum whisper and turned it into a shout, a cosmic symphony composed by the random vibrations of nothingness. Yet for all its explanatory power, inflation remains a theory with fierce debates. Some physicists argue it's too flexible, able to explain almost any observation by tweaking parameters, while others seek alternatives, like bouncing cosmologies where the Big Bang was a rebound from a prior collapse. Upcoming experiments like those measuring primordial gravitational waves could settle the matter, because if we're right about inflation, we're not just uncovering the universe's past, we're glimpsing the very mechanism that crafted reality from chaos. Hidden within the fabric of the cosmos, woven between galaxies and threading through the voids, lies another enigma: primordial magnetic fields. Unlike the magnets on your fridge, these are vast, ghostly structures stretching across millions of light years, their origins lost in the chaos of the early universe. We've known for decades that galaxies and galaxy clusters harbor magnetic fields traced by the way they twist the light from distant stars into subtle, swirling patterns. But how did they get there? The leading theory is as startling as it is elegant. These fields might be relics from the universe's infancy, imprinted in the first fractions of a second after the Big Bang. Imagine the universe in its first moments, a seething plasma of particles and energy. Turbulent motions in this primordial soup could have generated weak magnetic fields, like the dynamo in Earth's core, but on a cosmic scale. As the universe expanded and cooled, these fields might have been frozen into the fabric of space itself, stretching and amplifying over billions of years. Today, we see their fingerprints in the polarized light from ancient quasars, light that's been subtly altered as it travels through magnetized intergalactic space. It's as if the universe left behind invisible brushstrokes, a magnetic tapestry we're only now learning to read. But here's where it gets even more intriguing. These fields might have played a crucial role in shaping the cosmos. In the early universe, before stars ignited, pockets of gas needed to collapse to form the first structures. But gas is stubborn. It resists compression, spreading out unless something helps it clump together. Magnetic fields could have been that missing ingredient, acting like cosmic scaffolding to guide collapsing gas into denser filaments. Without them, the first stars might have taken far longer to ignite, delaying the birth of galaxies, and by extension, us. The hunt for these ancient fields is now ramping up with tools like the Square Kilometre Array, a next-generation radio telescope so sensitive it could detect the faintest whispers of magnetism from the dawn of time. By mapping how these fields twist the light from the earliest galaxies, scientists hope to glimpse their primordial origins, yet mysteries remain. If these fields are truly primordial, why haven't they decayed away over billions of years? Some theories suggest they're constantly regenerated by cosmic turbulence, like a river carving its own path through the void. Others propose even wilder ideas, that these fields are evidence of exotic physics in the universe's first moments, relics of a symmetry breaking that shaped the laws of nature itself. What's certain is that these invisible threads are more than cosmic decoration. They're a fundamental force woven into the story of the universe, from the birth of the first stars to the vast structures we see today. And just like dark matter and dark energy, they remind us that the cosmos is filled with hidden actors, quietly shaping reality in ways we're only beginning to understand. There's a reason physicists call neutrinos the universe's ultimate ghosts. These subatomic particles are so elusive they can pass through a light year of lead without a single interaction, yet they're everywhere, flooding the cosmos in countless trillions. Every second, billions slice through your body unnoticed, remnants of nuclear reactions in the sun and distant supernova. But here's the twist: neutrinos have a bizarre habit of shape-shifting mid-flight, transforming between three distinct flavors: electron, muon, and tau, a quantum magic trick called neutrino oscillation. And this discovery didn't just rewrite particle physics, it cracked open one of astronomy's oldest mysteries. Rewind to the 1960s when scientists first tried counting neutrinos pouring from the sun. According to theory, nuclear fusion in the sun's core should produce electron neutrinos in staggering numbers. Yet experiments like Ray Davis's Homestake mine detector, a tank of cleaning fluid buried underground, found only a third of the expected neutrinos. Where were the missing two-thirds? For decades, this solar neutrino problem stumped researchers. The answer came in 2002 when detectors like Japan's Super Kamiok and proved neutrinos weren't missing at all, they were simply disguising themselves. As these particles raced from the sun's core, some morphed into muon and tau neutrinos, undetectable by early experiments. But why does this matter? Because oscillations only happen if neutrinos have mass, a revelation that shattered decades of assumptions. The standard model of particle physics originally treated neutrinos as massless, like photons. They're tiny but non-zero mass forces physicists to revise entire theories, hinting at new particles or undiscovered forces. Imagine building a puzzle for years, only to realize the pieces don't fit because you missed an invisible layer beneath them. Today, detectors like IceCube, a cubic kilometer of Antarctic ice studded with sensors, hunt these cosmic chameleons by catching the faint flashes of light produced when a neutrino rarely collides with an atom. By tracking these flashes, scientists map neutrino flavors from sources like blazars or collapsing stars, revealing how they morph over cosmic distances. The implications are staggering. If neutrinos oscillate, they might hold clues to why the universe favors matter over antimatter, a bias that allowed our existence. Some theories even suggest sterile neutrinos, a hypothetical fourth flavor that could be dark matter. Every detection peels back another layer of the neutrino enigma, proving that even the most evasive particles can't hide their role in shaping the cosmos. Imagine you're floating in space, watching the Milky Way glide smoothly through the cosmos, except nothing about this motion is ordinary. Our galaxy is hurtling at 14 million miles per hour towards something we can't even see, yanked by a gravitational force so immense it defies explanation. Astronomers call it the Great Attractor, a mysterious region of space roughly 250 million light-years away, pulling entire galaxies toward it like a cosmic whirlpool. But here's the catch: we can barely study it because it lies hidden behind the Milky Way's own galactic plane, a dense shroud of stars, gas, and dust known as the zone of avoidance. This isn't just a minor blind spot. It's like trying to study a mountain while standing in a fog bank. The zone obscures nearly 20% of the visible sky, leaving the Great Attractor's true nature shrouded in mystery. Early glimpses came from X-ray and radio telescopes, which can pierce through the cosmic haze, revealing hints of massive galaxy clusters lurking in the darkness. These observations suggest the Great Attractor isn't a single object but a colossal knot in the cosmic web, a gravitational focal point where thousands of galaxies converge. To grasp its scale, picture the Laniakea supercluster, a sprawling network of 100,000 galaxies, including our own Milky Way, all flowing like rivers toward the Great Attractor. Laniakea, meaning immeasurable heaven in Hawaiian, spans 500 million light-years, with the Great Attractor acting as its gravitational heart. But even Laniakea is being tugged toward something larger, the Shapley supercluster, an even more massive structure 800 million light-years away. It's a cosmic game of tug-of-war, with our local universe caught in the middle. The real puzzle, what's generating this pull? Some theories point to dark matter, its invisible grip shaping the motion of galaxies. Others speculate about exotic phenomena like quantum fluctuations frozen into the fabric of space during the universe's infancy. Every new observation, from infrared surveys to gravitational mapping, chips away at the mystery, but the Great Attractor remains one of the most tantalizing enigmas in modern astronomy. It's a reminder that even as we map the cosmos, some forces refuse to be seen, their influence felt only in the silent drift of galaxies across the void. Black holes aren't just cosmic vacuum cleaners, they're existential riddles wrapped in event horizons. At first glance, they seem simple enough. Matter falls in, and thanks to their monstrous gravity, nothing escapes, not even light. But when you throw quantum mechanics into the mix, things get messy. Imagine tossing an encyclopedia into a black hole. According to Einstein's general relativity, that information is gone forever, crushed into the singularity. But quantum mechanics insists information can't just disappear, it must be preserved, even if scrambled beyond recognition. This clash of theories is the black hole information paradox, and it's been gnawing at physicists for decades. Enter Stephen Hawking's bombshell discovery in the 1970s. Black holes, he argued, aren't completely black. They slowly leak energy through Hawking radiation, a faint glow of particles born from quantum fluctuations near the event horizon. Given enough time, trillions upon trillions of years, a black hole would evaporate entirely. But here's the catch: Hawking originally thought this radiation carried no information about what fell in. If true, the encyclopedia's contents would be erased from the universe, violating quantum mechanics' sacred rule of information conservation. The physics community split. Some, like Hawking, accepted information loss. Others, like Leonard Susskind, fought back, arguing the universe couldn't just forget things. Then came the firewall paradox, a thought experiment so unsettling it made physicists question the nature of reality itself. Picture this: if information does escape via Hawking radiation, it can't just be a gentle trickle. Quantum mechanics demands that the radiation particles be entangled with both the black hole's interior and earlier radiation. But entanglement is monogamous. A particle can't be fully entangled with two things at once. To resolve this, theorists proposed a horrifying fix: a wall of searing energy just inside the event horizon, annihilating anything crossing it. This firewall would sever the entanglement, preserving information but turning black holes from smooth gateways into cosmic death traps. The implications are staggering. If firewalls exist, Einstein's vision of a falling observer peacefully crossing the event horizon, a cornerstone of general relativity, is wrong. Yet without firewalls, quantum mechanics might crumble. It's as if the universe handed us a jigsaw puzzle where the pieces fit only if we break half of them. Today, the debate rages on. Some theorists propose holographic solutions where information is encoded on the black hole's surface like a cosmic DVD. Others explore fuzzballs, string theories alternative to singularities, where black holes are tangled masses of energy preserving data in their structure. Every new idea pushes the boundaries of physics, forcing us to ask, is space-time fundamentally smooth or is it pixelated? Can quantum mechanics and gravity ever reconcile, or do we need a deeper theory? What makes this paradox so thrilling isn't just the mystery, it's the stakes. Solving it could reveal the hidden rules stitching reality together, proving whether information, the universe's ultimate currency, is truly eternal. Until then, black holes remain the ultimate cosmic locked room mysteries, daring us to crack their secrets. The cosmic microwave background, our oldest snapshot of the universe, should be the ultimate equalizer, a perfectly random canvas of hot and cold spots. But when scientists mapped it with satellites like WMAP and Planck, they stumbled on something unnerving. The fluctuations weren't entirely random. A peculiar axis, nicknamed the axis of evil, seem to align with the ecliptic plane of our solar system, as if the universe had quietly picked a favorite direction. This wasn't just a minor quirk, it was a potential crack in one of astronomy's bedrock principles, the Copernican idea that Earth holds no special place in the cosmos. At first glance, the alignment sounds like cosmic pareidolia, the human tendency to see patterns in noise. After all, the CMB is a tapestry woven from quantum fluctuations, and randomness can sometimes look ordered. But statistical analyses revealed the odds of this alignment happening by chance were less than 1 in 1,000. That's like shuffling a deck of cards and dealing yourself a perfect sequence 50 times in a row. The implications sent shockwaves through cosmology. If the universe does have a preferred axis, it could mean our understanding of inflation, the rapid expansion after the Big Bang, is missing a crucial ingredient. Maybe inflation wasn't perfectly uniform, leaving behind subtle ripples in spacetime's fabric. Or perhaps dark energy isn't evenly distributed, tugging the cosmos into alignment like an invisible magnet. Then there's the wilder possibility that we're seeing evidence of a pre-Big Bang universe. Some theories suggest our cosmos might be one bubble in an endless multiverse, and the axis marks where our bubble brushed against another, leaving a cosmic bruise. Others propose it's a relic of quantum entanglement stretching across the early universe, knitting reality together with hidden threads. But here's where skepticism kicks in. The axis of evil might not be a cosmic conspiracy, it could just be contamination. Our solar system's motion creates a Doppler shift in the CMB, a subtle blurring known as the kinematic dipole. If not perfectly accounted for, this could fake a preferred direction. Then there's galactic dust, which scatters light in ways that mimic alignment. Even the Milky Way's magnetic field might twist CMB photons, leaving phantom patterns. The debate boils down to a battle between two worldviews, one where the universe is fundamentally lopsided, and another where human error and statistical flukes conspire to fool us. Future experiments like next-generation CMB telescopes with 10 times the resolution could settle the argument by peeling away every layer of interference. Until then, the axis of evil lingers, a spectral fingerprint on the edge of discovery or delusion. Whether it's a flaw in our maps or a crack in reality's foundation, one thing's certain: the universe loves keeping us guessing. If there's one phenomenon that makes physicists question the very nature of reality, it's quantum entanglement, the bizarre, instantaneous connection between particles that defies all classical intuition. Picture two electrons born from the same quantum event, spiraling away from each other across the cosmos. No matter how far they travel, whether separated by inches or light years, measuring one instantly determines the state of its partner, as if space and time simply don't apply to their relationship. Einstein famously called this spooky action at a distance, dismissing it as evidence that quantum theory must be incomplete. Yet decades of meticulous experiments have proven entanglement isn't just real, it's one of the universe's most fundamental features. The smoking gun came in the 1960s when physicist John Bell devised a mathematical test to settle the debate. Bell's theorem showed that if hidden variables, secret instructions guiding particles' behavior existed, their correlations would never exceed a certain limit. But when scientists like Elaine Aspect ran the experiments in the 1980s, particles smashed that limit every time. Their results revealed correlations so strong they could only be explained by genuine, instantaneous influence, violating the principle of locality, the idea that objects can only be influenced by their immediate surroundings. It's as if the universe operates with a hidden layer where distance is irrelevant, a quantum gossip network humming beneath the surface of reality. Here's where it gets truly mind-bending. Entanglement isn't some rare quantum party trick, it's everywhere. When sunlight hits your skin, the photons are entangled with their counterparts back in the sun's core. The molecules in your coffee owe their stability to entangled electrons. Some theories even suggest entanglement might have sculpted the early universe. During cosmic inflation, quantum fluctuations entangled particles across regions that would later stretch to opposite ends of the observable cosmos. Today, those primordial threads could still link galaxies billions of light-years apart, weaving space itself into a vast quantum web. The implications ripple far beyond theory. Quantum computers harness entanglement to perform calculations impossible for classical machines, while encrypted networks use it to create unhackable codes. But the deepest mystery remains: how does nature enforce this eerie connection? One radical answer comes from holographic theories, where entanglement doesn't happen in space but actually creates space, stitching the fabric of space-time together like cosmic Velcro. Others propose retrocausality, that particles communicate backward through time to coordinate their states. Yet for all our progress, entanglement still taunts us. It challenges our notions of cause and effect, space and separateness, even the nature of objects themselves. Because if two particles can act as one across cosmic distances, maybe individuality is just an illusion, a fleeting pattern in a universe far more interconnected than we ever imagined. One of the most heated debates in modern cosmology revolves around a single number: how fast the universe is expanding. For decades, astronomers assumed this value, the Hubble constant, would be straightforward to pin down. Yet today, two of science's most reliable methods for measuring it disagree so sharply that some call it the Hubble tension, a crisis that could upend our understanding of cosmic history. The first method relies on the cosmic microwave background, that ancient afterglow of the Big Bang. By analyzing tiny temperature fluctuations in this radiation, satellites like Planck calculated an expansion rate of about 67 kilometers per second per megaparsec. Think of it like measuring the speed of a car by studying tire tracks it left years ago. It's indirect but precise. Meanwhile, the second method uses supernova as cosmic mile markers. By observing how these exploding stars dim with distance, teams like the SH0ES project landed on a faster value, 73. That 6-kilometer gap might seem small, but statistically, it's like two clocks disagreeing by hours after just minutes. So why does this matter? Because these aren't just competing measurements, they're conflicting visions of the universe. If the CMB's slower rate is correct, our models of cosmic evolution might need tweaking. But if supernovae are right, we could be missing something fundamental, like an unseen force tweaking the universe's expansion. Enter early dark energy, a hypothetical phenomenon that might have briefly surged during the cosmos's first 300,000 years, subtly altering the CMB's imprint. Picture blowing up a balloon in bursts, an initial quick push, then steady inflation. Early dark energy would leave the CMB thinking expansion was slower overall, while letting supernovas see today's faster pace. Then there's the nuclear option, new physics. Some theorists suggest gravity itself might behave differently on cosmic scales, weakening over time or interacting with dark matter in unexpected ways. Others propose that neutrinos, those ghostly particles we still barely understand, could be throwing off the measurements if they're more massive than predicted. The boldest ideas even flirt with extra dimensions leaking gravity into unseen realms. What makes the Hubble tension so electrifying isn't just the disagreement, it's the stakes. Resolving it could reveal hidden layers of reality, forcing us to rewrite cosmology's rulebook. Telescopes like JWST are now hunting for pristine Cepheid stars, while next-generation CMB experiments aim to spot early dark energy's fingerprints. Until then, this cosmic standoff remains a thrilling reminder. The universe's simplest questions often have the most surprising answers. The universe has a startling secret: it shouldn't exist. At least not as we know it. According to the laws of physics, the Big Bang should have created equal amounts of matter and antimatter particles, identical in mass but opposite in charge. When matter and antimatter meet, they annihilate in a flash of energy, leaving nothing behind. So why didn't the early cosmos cancel itself out? Why does anything, stars, planets, us, remain at all? This is the enigma of baryon asymmetry, one of the universe's deepest puzzles, and the answer might lie in a tiny cosmic betrayal known as CP violation. Let's rewind to the universe's first moments, a seething chaos of quarks, antiquarks, and radiation. For every billion matter-antimatter pairs that annihilated, a single quark somehow survived. That 1 in a billion imbalance is all that separates us from oblivion. But how? In the 1960s, physicists James Cronin and Val Fitch found a clue in the decay of kaons, exotic particles that violated what was then a sacred rule: charge parity symmetry, or CP. Simply put, CP symmetry means the laws of physics should treat matter and antimatter as mirror images. But kaons decayed slightly differently than their antimatter counterparts, as if the universe had a hidden preference for matter. Fast forward to today, and experiments at CERN ALICE detector are probing this asymmetry with unprecedented precision. By smashing lead nuclei at nearly light speed, ALICE recreates the quark-gluon plasma of the early universe, a soup where quarks and antiquarks roamed freely. The goal: to spot even the faintest deviations in how matter and antimatter behave, clues that might explain why one outmuscled the other. Already, ALICE has observed CP violation in heavy quarks, suggesting the imbalance might be baked into the fabric of reality itself. But quarks might not be the whole story. Enter leptogenesis, a theory where the matter-antimatter rift began with neutrinos. These ghostly particles could have decayed asymmetrically in the early universe, spawning more electrons than positrons. Over time, that lepton imbalance might have seeped into the quark world through quantum processes, tilting the scales toward matter. It's a cosmic domino effect, one that could explain why we're here at all. The stakes couldn't be higher. If baryon asymmetry stems from particle physics we've yet to discover, it could point to new forces, extra dimensions, or even a shadow universe of antimatter galaxies. Or perhaps the answer lies in the vacuum itself, where quantum fluctuations favored matter in the universe's first trillionth of a second. Whatever the truth, solving this riddle wouldn't just explain our existence, it would rewrite the story of everything. Because in the end, we're not just stardust, we're the survivors of a cosmic war, the remnants of a symmetry broken long before the first stars awoke. Rising like colossal chimneys from the heart of the Milky Way, two gargantuan bubbles of gamma-ray light stretch 25,000 light-years into space, one above the galactic plane, one below. These are the Fermi bubbles, named after the telescope that spotted them in 2010, and they're unlike anything else in our galaxy. Imagine two orbs, each glowing with the energy of 100,000 supernova, their edges razor-sharp against the darkness. They're remnants of some cataclysmic event, a cosmic scream frozen in time. But here's the puzzle: what could unleash such fury? One leading suspect is our galaxy's supermassive black hole, Sagittarius, a star. Though quiet today, it might have erupted 4 million years ago in a titanic outburst known as an active galactic nucleus, or AN, event. Picture a black hole feasting on a colossal meal of gas and stars, its accretion disk spinning so fast it becomes a particle accelerator, shooting jets of plasma straight up and down like a cosmic fire hose. Those jets could have punched through the galaxy's gas, carving out the bubbles and filling them with high-energy particles that still glow in gamma rays. Supporting this idea are the so-called Fermi cocoons, regions of even more intense radiation nestled near the bubble's bases like scorch marks from the black hole's jets. But there's a twist. Some theorists argue the bubble's symmetry is too perfect for a chaotic AGN burst. Instead, they might be evidence of something far stranger: dark matter annihilating itself. If dark matter particles like WIMP or axions collide and destroy each other near the galaxy's center, they'd release gamma rays as a byproduct. The bubble's crisp edges could trace the boundary where dark matter's density drops off, like a candle flickering only where the wax is thickest. It's a tantalizing thought. These structures might be the first visible signature of the invisible stuff holding galaxies together. yet neither theory fits perfectly. The Aegean scenario struggles to explain why no other galaxies have bubbles so bright, while dark matter models can't yet account for the bubble's sheer energy. Then there's the middle ground. Maybe both forces are at play. Perhaps Sagittarius, a star's eruption, stirred up dark matter, triggering annihilations that supercharge the bubble's glow. For now, the Fermi bubbles remain a cosmic riddle, a reminder that even our own backyard holds mysteries as deep as the farthest quasars. New telescopes like the Cherenkov Telescope Array aim to study their high-energy light in unprecedented detail, hunting for the fingerprints of black holes or particles we've yet to name. Whatever the answer, these towering relics prove one thing: the Milky Way's past was anything but peaceful. Most of us picture the Milky Way drifting through space like any other galaxy, surrounded by neighbors, part of the cosmic crowd. But what if we're actually floating in a cosmic desert, a void so vast it's warping our view of the entire universe? That's the startling idea behind the KBC void, named after astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, who first pieced together the evidence. Our galaxy isn't just in space, it's perched inside a bubble of emptiness stretching over 2 billion light-years across, the largest known underdensity in the observable cosmos. The clues began piling up when astronomers noticed something odd about nearby galaxies. Compared to the universe's average, our cosmic backyard seemed suspiciously quiet, with fewer galaxies clustering around us than expected. Then came measurements of Type Ia supernova, the same stellar explosions used to track the universe's expansion. These cosmic beacons appeared slightly brighter than they should, as if space itself had stretched more than usual during their light's journey to us. The explanation: if we're inside a void, the gravitational tug from surrounding denser regions would pull matter outward, creating a local expansion rate faster than the universe's average. It's like being in a valley while the rest of the world slopes uphill. Everything outside seems to move away faster because gravity's grip is weaker where we stand. This leads to the million-light-year question: could the KBC void explain the Hubble tension, that gnawing discrepancy in cosmic expansion rates? Some theorists think so. If our measurements are skewed by this underdensity, the local supernova-based value, 73 kilometers per second per megaparsec, might be overestimating the true universal rate. Meanwhile, the CMB's slower value, 67, would remain untouched, representing the universe's baseline. It's a tempting fix except for one problem. For the void to account for the full tension, it'd need to be far emptier than current observations suggest. Most models show it's only about 20% underdense, not enough to bridge the gap alone. Then there's the statistical elephant in the room. Are we sure this void is real, or is it just a fluke in our galactic neighborhood? After all, the universe is clumpy. Dense filaments and empty voids are part of its structure. Finding ourselves in a modest underdensity isn't shocking, but a void this size pushes the limits of cosmic variance. Simulations suggest such giants should be exceedingly rare in our standard model of cosmology. If confirmed, the KBC void might mean the universe is lumpier than we thought, or that dark energy behaves differently in voids versus clusters. The debate is far from settled. Upcoming galaxy surveys like the Dark Energy Spectroscopic Instrument, DAISY, aim to map millions of galaxies in 3 dimensions, revealing whether the void's edges hold more galaxies than we've seen. Other teams are hunting for secondary effects, like subtle temperature shifts in the CMB caused by the void's gravitational pull. What makes this cosmic empty space so fascinating isn't just its size, it's the philosophical punchline. For centuries, we've fought the assumption that Earth holds a special place in the universe. Now, we might have to grapple with the opposite. Our galaxy's unspecial position in a rare bubble of nothingness could be skewing how we see everything. Whether the KBC void solves the Hubble tension or not, it's a humbling reminder. Sometimes, to understand the cosmos, we first have to question our place within it. Hidden in the constellation Boötes lies one of the most unsettling places in the cosmos, a yawning abyss so vast it defies comprehension. The Boötes void spans 330 million light-years, a staggering emptiness where galaxies should cluster by the thousands, yet fewer than 60 have been found. To grasp its scale, picture this. If the Milky Way were a grain of sand, the Boötes void would be a hollow sphere stretching from New York to Los Angeles, with almost nothing inside. Astronomers stumbled upon this cosmic desert in the 1980s while mapping galaxy distributions, expecting the universe's structure to resemble a sponge, filaments and clusters woven around moderately empty voids. But the Boötes void wasn't just a gap, it was a bottomless pit in the cosmic web, a place where structure itself seemed to unravel. What makes this void so unnerving is how it breaks the rules. According to standard cosmology, the early universe's quantum fluctuations should have created a relatively even distribution of dense regions and voids during inflation. Simulations predict voids no larger than 150 million light-years, yet the Boötes void dwarfs that. It's as if someone took a cosmic vacuum to space, sucking out matter on scales that shouldn't be possible. Some speculate it might be the ghost of an ancient collision between our universe and another bubble in the multiverse, leaving behind a scar of nothingness. Others wonder if dark energy's repulsive force is sculpting voids faster than we thought, stretching them into unnatural sizes over billions of years. Then there's the eerie missing galaxy problem. The handful of galaxies found in the void aren't just sparse, they're oddly isolated, with few neighbors to gravitationally bond with. Many are void galaxies, a rare breed that evolves in isolation, lacking the frequent collisions and gas inflows that shape galaxies in denser regions. These loners tend to be smaller, bluer, and richer in young stars, like desert flowers clinging to life in a wasteland. Their very existence hints that the void isn't entirely empty, just impossibly stretched, with galaxies so far apart they might as well be in separate universes. The Boötes void isn't just a curiosity, it's a stress test for our cosmic models. If such megavoids are more common than we think, they could upend our understanding of dark matter's role in structuring the universe. Perhaps dark matter isn't distributed as smoothly as simulations suggest, or maybe gravity behaves differently in these vast deserts. Upcoming surveys like the Vera Rubin Observatory's 10-year sky scan will hunt for more of these voids, probing whether Boötes is a freak anomaly or a sign that the cosmos hides deeper layers of chaos. But here's the most humbling thought. Voids like Boötes aren't just empty space, they're windows into the universe's limits. Light from galaxies beyond the void must pass through this emptiness to reach us, subtly warping along the way due to the void's weaker gravity. By studying these distortions, astronomers can map the void's true shape, weighing the absence within. It's a reminder that in the grand tapestry of the cosmos, even nothingness has a story to tell if we're willing to listen. In the cosmic microwave background, that primordial glow from the dawn of time, most temperature variations are tiny fractions of a degree, the faint echoes of quantum noise. But one patch defies all expectations, the CMB cold spot, a region in the constellation Eridanus where temperatures plummet far beyond what standard cosmology predicts. Stretching nearly 2 billion light-years across, this cosmic chill is so extreme that its odds of existing in our universe's model are less than 1 in 50. So what's casting this shadow on the infant cosmos? The answer might rewrite our understanding of reality itself. One leading theory points to a supervoid, an unimaginably vast bubble of emptiness where galaxies are eerily sparse. If such a void existed along our line of sight, photons from the CMB passing through it would lose energy as they climbed out of its gravitational well, a phenomenon called the integrated Sachs-Wolf effect. Think of it like rolling a marble uphill. It slows down, losing kinetic energy. For light, that energy loss translates to a slight redshift, cooling the CMB in that direction. But here's the catch. To explain the cold spot's depth, This void would need to be so enormous and empty that it strains the limits of cosmic structure. Surveys like the Dark Energy Survey have indeed found a sparse region there, but it's not nearly large or empty enough to account for the anomaly. It's as if we're seeing the shadow of a ghost, something far stranger than mere nothingness. That's where exotic physics enters the picture. Some theorists propose the cold spot could be a cosmic texture, a topological defect in spacetime left over from the universe's high-energy infancy. Picture the early cosmos as a bubbling stew of phase transitions, like water freezing into ice. Occasionally, these transitions could have created tangled knots in spacetime itself, regions where the fabric of reality twists into a unique configuration. If one such knot decayed near us, it would have left behind a telltale temperature dip in the CMB. The cold spot's sharp edges and unusual polarization patterns fit this idea eerily well, though conclusive proof remains elusive. Then there's the wildest possibility. The cold spot might be a bruise from a collision with another universe. In certain multiverse models, our cosmos isn't alone but floats in a higher dimensional bulk, occasionally brushing against neighboring bubble universes. Such a collision would inject energy unevenly into our universe, leaving behind a cold imprint in the CMB. It's a radical idea but not untestable. If true, the cold spot's polarization data should show distinct swirls like fingerprints from a cosmic fist bump. Future CMB experiments like the Simons Observatory aim to hunt for these subtle patterns, turning speculation into hard evidence. For now, the cold spot remains one of cosmology's most tantalizing enigmas. Whether it's a void, a space-time defect, or a window into the multiverse, its existence challenges us to question the universe's fundamental architecture. Because sometimes the deepest mysteries aren't written in the stars, but in the cold, quiet gaps between them. Somewhere in the distant cosmos, an unfathomable burst of energy erupts. A flash of radio waves packing more power than the sun emits in 80 years, all compressed into a few milliseconds. This is a fast radio burst, or FRB, one of the most enigmatic signals ever detected from deep space. Since their discovery in 2007, these cosmic fireworks have baffled astronomers. They arrive without warning, flickering across the sky like phantom lighthouses, their origins veiled by billions of light-years of distance. But what could possibly unleash such staggering energy? And why do some of these bursts repeat like clockwork, while others vanish without a trace? The plot thickened in 2016 when astronomers caught the first repeating FRB, a source now catalogued as FRB 121102. Unlike the one-offs, this object sporadically fires off bursts, sometimes dozens in a row, each as intense as the last. It's like finding a volcano that doesn't just erupt once, but spews fire at random intervals for years. The discovery shattered early theories that FRBs were produced by cataclysmic, one-time events like neutron star collisions or black hole births. Instead, repeaters hinted at an engine capable of sustaining these explosions over time, something with the durability and power to fire off multiple salvos across cosmic epochs. Enter magnetars, the universe's ultimate cosmic tantrum throwers. These are neutron stars with magnetic fields so intense they could strip the electrons from your atoms from 1,000 kilometers away. When a magnetar's crust cracks under the strain of these fields, it releases a starquake, a seismic event so violent it can hurl a tsunami of charged particles into space, sparking a firestorm of radio waves. In 2020, astronomers got their strongest evidence yet when a magnetar in our own galaxy, SGR 1935+2154, emitted an FRB-like burst. The match wasn't perfect. This burst was slightly weaker than its extragalactic cousins, but it proved magnetars could produce the right kind of fireworks. Yet not all FRBs fit the magnetar mold. Some bursts exhibit bizarre polarization patterns, their radio waves twisted as if they've traversed monstrous magnetic fields, far stronger than any magnetar we've seen. Others arrive with such precision they've been proposed as cosmic yardsticks, their signals subtly altered by the tenuous gas between galaxies. Then there's FRB 190520b, a repeater that seems to flicker on a predictable cycle, flaring every 157 days like a cosmic metronome. Such regularity points to an orbital origin, perhaps a magnetar locked in a deadly dance with a black hole or a massive star, its outbursts triggered by periodic tidal stresses. The real challenge lies in the distances. Most FRBs originate billions of light-years away, their signals stretched and scrambled by the expanding universe. To catch them in the act, telescopes like CHIME in Canada scan vast swaths of sky around the clock, pinpointing bursts with millisecond precision. Meanwhile, projects like the Deep Synoptic Array in California aim to localize FRBs to their host galaxies, hunting for clues in the environments that spawn them. Already, we've traced some to distant spiral galaxies, others to dense star-forming regions, but no single setting explains them all. What makes FRBs so electrifying isn't just their mystery, it's what they reveal about the universe's hidden layers. Every burst is a messenger, its signal encoded with secrets about the intergalactic medium it traversed. Some pulses arrive split into multiple frequencies, a fingerprint of the turbulent plasma they passed through. Others carry hints of cosmic missing matter, the elusive baryons thought to lurk in the voids between galaxies. And if some FRBs truly originate from magnetars, their extreme physics could offer a lab for testing relativity under conditions impossible to replicate on Earth. For now, each new detection peels back another layer of the puzzle. Are FRBs the death cries of exotic stars, the birth pangs of new physics, or something stranger still? With every burst, the cosmos seems to whisper, but we're only just learning to listen. On the night of August 15, 1977, a radio telescope at Ohio State University picked up something extraordinary, a 72-second burst of radiation so powerful, so precise, that the astronomer who discovered it scribbled, "Wow." In the margin of the data printout, that single word gave the signal its name, and for decades, it's been the closest thing we have to a cosmic hello. A blip of radio waves bearing all the hallmarks of an intelligent broadcast. The signal was narrowband, centered on the hydrogen line frequency of 1420 MHz, a logical choice for any civilization trying to announce its presence, since hydrogen is the most abundant element in the universe. And then, just as suddenly as it appeared, it vanished, never to be heard again. For years, the WOW signal stood as a tantalizing anomaly, a beacon from the stars that defied natural explanation. But in 2016, a controversial new theory emerged. What if the signal wasn't alien at all, but something far more mundane, a pair of passing comets? Astronomer Antonio Paris proposed that the comets 266P/Christensen and 335P/Gibbs, which happened to be transiting the same patch of sky in 1977, could have reflected solar radiation, creating the illusion of a narrowband signal. Hydrogen clouds surrounding the comets might have emitted at the exact frequency the telescope was monitoring. At first glance, it was a neat solution except for one glaring problem. Follow-up observations when the comets returned in 2017 found no such emissions. The silence was deafening, leaving the WOW signal's origin as mysterious as ever. Then there's the timing. The signal's intensity peaked for exactly 72 seconds, matching how long the telescope's feed would have scanned that particular point in the sky. It's as if someone or something knew exactly how to maximize its visibility to us. And while natural phenomena like pulsars or quasars can produce radio bursts, none match the WOW signal's combination of narrow bandwidth, perfect frequency, and one-time-only appearance. Even if comets or some other cosmic fluke were responsible, the odds of all these factors aligning by chance are astronomically slim. The search for answers has only grown more sophisticated. Modern projects like Breakthrough Listen now scour millions of radio channels simultaneously, hunting for signals that resemble the WOW event's distinctive fingerprint. Meanwhile, researchers have re-examined the original data with 21st-century tools, ruling out terrestrial interference or satellite reflections. What's left is a signal that refuses to be explained away, a cosmic whisper that, whether it was a comet's glint or an alien handshake, continues to remind us how much we still don't know about the universe's quietest corners. The WOW signal endures not just as a scientific puzzle, but as a cultural touchstone, a proof that the cosmos occasionally winks at us, leaving us to wonder if we're alone or simply not listening closely enough. Until the next one arrives, it remains a humbling reminder. Sometimes the universe's most profound mysteries come in 72-second packages. When NASA Pioneer 10 and 11 spacecraft drifted beyond the edge of our solar system, scientists expected them to obey the immutable laws of gravity, slowing slightly as they escaped the sun's pull, but otherwise coasting predictably into the void. Instead, something bizarre happened. Both probes began decelerating faster than equations could account for, as if an invisible hand were tugging them backward. This tiny but persistent deviation became known as the Pioneer Anomaly, a cosmic mystery that haunted physicists for decades. At first glance, the numbers seemed insignificant, a deceleration of about 9 trillionths of a meter per second squared. But over years of interstellar travel, that minuscule drag added up, pushing the Pioneers hundreds of kilometers off course. Theories erupted like supernova. Was it rogue dark matter, a flaw in Einstein's general relativity, or something stranger, an undiscovered force acting across the emptiness of space? The breakthrough came from an unexpected corner: heat. Not cosmic radiation or solar winds, but the faint infrared glow of the probes themselves. Every electrical component aboard the Pioneers generated warmth, and that warmth radiated outward as photons. While most of this thermal energy escaped harmlessly into space, scientists realized a fraction was bouncing off the spacecraft's dish-shaped antennas, creating a tiny but measurable recoil like a garden sprinkler pushing backward as water jets forward. When researchers meticulously modeled this effect in 2012, the numbers aligned almost perfectly with the anomaly. Case closed, or so it seemed. Yet for some, the thermal explanation left uneasy gaps. Why did the deceleration remain so constant across billions of kilometers, even as onboard power and thus heat fluctuated? And why didn't other spacecraft like Voyager exhibit the same drift? The answer might lie in design differences. Pioneer's spin-stabilized body and large antenna made it uniquely sensitive to thermal recoil, but skeptics point to lingering discrepancies. Could there still be a whisper of new physics hidden in the data, a shadow of some deeper cosmic rule we've yet to grasp? Today, the Pioneer Anomaly stands as a cautionary tale, a reminder that even the smallest deviation can unravel assumptions about the universe. It's also a testament to scientific grit, decades of poring over old telemetry, chasing down every possible explanation, no matter how mundane. But perhaps the most thrilling possibility is the one we can't yet prove, that somewhere in those residual uncertainties, the cosmos is still hiding a clue, waiting for the next generation of starfarers to uncover it. It starts with a simple maneuver, one so routine that spacecraft have performed it for decades: the gravity assist. By skimming past a planet, a probe can steal a fraction of its orbital energy, slingshotting itself deeper into space. The math behind these flybys is precise, honed by Newton's laws and refined by Einstein's relativity. Yet something keeps going wrong. Take NASA Galileo probe in 1990. As it swung past Earth for a gravity boost, something nudged its speed just 4 millimeters per second faster than predicted. A fluke, perhaps. Then it happened again with the Near spacecraft in 1998. And again with Rosetta in 2005. Each time, the anomaly was tiny, less than the weight of a snowflake's influence, but undeniable. Across 15 flybys, these unaccounted speed changes became known as the flyby anomaly, a glitch in the cosmic rulebook that no one could explain. At first, scientists blamed mundane factors: atmospheric drag, Earth's uneven gravity, even thermal radiation from the spacecraft, but the numbers refused to add up. The speed shifts didn't correlate with altitude or trajectory. Some probes gained velocity, others lost it, and the effect seemed to vanish during certain flybys, as if whatever caused it had flickered out. That's when the theories turned radical. Could Earth be enshrouded in a halo of dark matter, its invisible gravity tweaking the probe's paths? If so, the anomaly's unpredictability might stem from our planet plowing through uneven dark matter currents, like a ship leaving ripples in an unseen sea. Others proposed modifications to gravity itself, suggesting Einstein's equations break down at planetary scales. A heresy in physics, but one that would explain why the anomaly only appears near massive bodies. Then there's the wildest idea: the Earth's rotation might be warping spacetime more than we thought. According to general relativity, a spinning mass drags spacetime around it like honey clinging to a spoon. This frame-dragging effect is subtle, but some models suggest it could vary based on a probe's approach angle, imprinting those tiny speed changes. The trouble is, none of these explanations fully fit. Dark matter halos should affect satellites too, yet they show no such anomalies. Modified gravity struggles to explain why the effect isn't seen at larger scales. And frame dragging, while real, is orders of magnitude too weak to account for the measurements. Enter Juno. In 2013, NASA deliberately designed its Jupiter-bound trajectory to test the anomaly, threading it past Earth with exquisite precision. The result: no anomaly at all. It was as if the universe had erased its own tracks, leaving physicists staring at equations that refused to misbehave. Today, the flyby anomaly remains one of those quiet cosmic puzzles, too small to dismiss, too inconsistent to solve. Maybe it's a quirk of unseen physics, a shadow of something deeper lurking in the math. Or maybe, like so many mysteries, it's a reminder that even our best models are approximations, sanded smooth by the universe's rough edges. Until the next probe swings by, the anomaly hangs in the air, less a question than a whisper, hinting that gravity's final chapter hasn't been written yet. In October 2017, astronomers spotted something extraordinary: a strange, tumbling object hurtling through our solar system at blistering speeds. Named Oumuamua, Hawaiian for scout, it was the first confirmed visitor from interstellar space, a cosmic wanderer passing through on its way to who knows where. But as telescopes tracked its trajectory, something didn't add up. Instead of following a predictable path shaped by the sun's gravity alone, Oumuamua accelerated ever so slightly, as if nudged by an unseen force. At first, scientists assumed it was outgassing, the same process that gives comets their glowing tails. When icy comets warm up near the sun, they release jets of gas and dust, creating a gentle push that alters their orbit. But here's the problem: Oumuamua showed no visible coma or tail. Not a single telescope caught even a wisp of dust or gas being ejected. If it was outgassing, it was doing so in a way we'd never seen before, leaving no trace of the very process supposedly driving its acceleration. That's when the explanations turned radical. Harvard astrophysicist Avi Loeb proposed an idea that sent shockwaves through the scientific community. What if Oumuamua wasn't a hunk of rock or ice at all, but an artificial object, a fragment of alien technology, perhaps a defunct light sail? Light sails, thin reflective sheets propelled by sunlight or lasers, are a concept we're actively developing ourselves, like the Breakthrough Starshot initiative. A tumbling, pancake-shaped sail could explain Oumuamua's unusual brightness variations and its unexpected acceleration without needing outgassing, but not everyone's convinced. Critics argue that invoking extraterrestrial tech is a last resort, a violation of Occam's razor, the principle that simpler explanations are more likely. They point to exotic but natural possibilities, like Oumuamua being a shard of hydrogen ice. Hydrogen icebergs, theoretically born in the coldest depths of interstellar space, could sublimate under sunlight, producing an invisible thrust without leaving dusty traces. The catch: no one's ever observed a hydrogen iceberg, and it's unclear if they could survive the journey between stars. Then there's the shape. Radar observations suggested Oumuamua was oddly elongated, perhaps 10 times longer than it was wide, an extreme ratio for any known asteroid or comet. If real, this needle-like form would be unprecedented in our solar system, but some researchers caution that the data was limited. Oumuamua might have been more like a flattened disk, tumbling in a way that fooled our instruments. The debate rages because Oumuamua is gone, streaking out of reach before we could study it closely. Future telescopes, like the Vera Rubin Observatory, might spot more interstellar visitors, giving us a second chance to crack the mystery. Until then, this cosmic enigma lingers, a reminder that sometimes the universe sends us puzzles wrapped in riddles, daring us to think beyond the known. Neutrons are the shy hermits of the atomic world, content to huddle inside atomic nuclei, rarely venturing out alone. Yet in rare, extreme environments like neutron stars, they briefly escape their proton partners, creating bizarre, fleeting states of pure neutron matter. Now imagine a particle so unstable it shouldn't exist even there. 4 neutrons bound together in a single, gossamer-thin package. This is the tetraneutron, a nuclear ghost so controversial its very existence would rewrite the textbooks. For decades, physicists dismissed the idea outright. According to the Pauli exclusion principle, identical particles like neutrons can't occupy the same quantum state simultaneously. While 2 neutrons can temporarily pair up inside certain unstable nuclei, adding a third or fourth should cause this fragile arrangement to implode instantly. It's like trying to balance 4 magnets all repelling each other. Nature abhors the configuration. That's why the first claimed tetraneutron detection in 2001 sent shockwaves through the physics community. A French team firing beryllium nuclei at a carbon target observed signatures consistent with a 4-neutron cluster, surviving for a mere 10 to the power of -22 seconds before disintegrating. Skeptics erupted, arguing the signal could just be random neutron noise. But in 2016, a Japanese team replicated the results with improved precision, reigniting the debate. If confirmed, the tetraneutron would force a radical rethink of nuclear forces. The strong interaction that binds protons and neutrons is finely tuned for pairs and triplets, not quartets. Its existence might hint at undiscovered resonances or even a new branch of neutron-rich matter. Picture neutron stars occasionally ejecting tetraneutron sparks, or supernova seeding the cosmos with these ephemeral particles. Some theories even suggest tetraneutrons could form the core of an entirely new class of exotic, unstable elements, ones with no protons at all. Yet the hunt is fraught with pitfalls. Detecting something that vanishes in a septillionth of a second requires trapping clues from the debris of high-energy collisions. Recent experiments at accelerators like Riken in Japan and Ganil in France use advanced detectors to spot the telltale gamma-ray flashes or recoiling fragments that might betray a tetraneutron's brief existence. Each new result walks a tightrope between statistical fluke and revolutionary discovery. What makes this search so electrifying isn't just the particle itself, it's what it represents. The tetraneutron dangles the possibility that our understanding of nuclear glue is incomplete, that neutrons might briefly dance in forbidden configurations under extreme conditions. Whether it's ultimately proven real or relegated to the graveyard of tantalizing anomalies, it reminds us that the atomic nucleus still holds secrets, and that sometimes the most unstable things shine the brightest light. The proton is supposed to be one of the most well-understood particles in existence, a tiny sphere of positive charge at the heart of every atom. but in 2010, physicists made a discovery that sent shockwaves through the field. Depending on how you measure it, the proton's radius seems to change. The discrepancy centers on muonic hydrogen, an exotic form of hydrogen where the electron is replaced by its heavier cousin, the muon. When scientists fired lasers at these atoms to study their energy levels, they found the proton's radius was 4% smaller than the accepted value from decades of electron-based measurements. 4% might sound trivial, but in the ultra-precise world of quantum electrodynamics, the theory governing how light and matter interact, it's a glaring inconsistency. Here's why this matters. QED has been called the most accurate theory in science, predicting phenomena like the magnetic moment of electrons to mind-bending precision. But its equations depend critically on the proton's size. If that size shifts based on which particle orbits its muon or electron, it implies something fundamental is missing from our understanding. Imagine weighing yourself on two scales and getting wildly different numbers, then realizing the flaw isn't in the scales but in gravity itself. That's the scale of the crisis the proton radius puzzle presents. The leading explanation involves virtual particles fleeting quantum fluctuations that pop in and out of existence around protons. These particles subtly alter the proton's effective size, and muons, being 200 times heavier than electrons, might probe this cloud of virtual activity differently, feeling a smaller radius. Some theories even suggest unknown forces between muons and protons could be at play, or that the proton isn't a perfect sphere but a shape-shifting entity that appears different when scrutinized by particles of varying masses. For years, the puzzle deepened. Electron-based experiments like the classic Lamb shift measurements stubbornly held to the larger radius, while muonic hydrogen insisted on the smaller one. Then, in 2017, a breakthrough. A team at York University measured regular hydrogen using a novel laser technique and got a result much closer to the muonic value. Suddenly, the discrepancy wasn't between muons and electrons, but between old and new methods. Was the smaller radius the real one all along? The implications ripple far beyond atomic physics. If QED needs adjusting to account for this anomaly, it could hint at gaps in the standard model, or even new particles lurking just beyond our current energy thresholds. Meanwhile, the precision required to resolve the puzzle has pushed experimental technology to its limits, with teams now using spectroscopy so exact it could detect a human hair's width across the distance to the moon. What makes this debate so captivating isn't just the scientific stake, it's the reminder that even the most familiar building blocks of reality can still surprise us. The proton, that textbook staple, might be hiding layers we've yet to unravel, whispering secrets about the universe's deepest rules through the language of vanishingly small numbers. And until the final measurement is made, the puzzle stands as a testament to science's endless frontier, where every answer births new questions and certainty is always provisional. Deep beneath the suburbs of Chicago, inside a sprawling complex of particle accelerators and detectors, scientists are chasing a ghost, a tiny wobble in the behavior of a subatomic particle that could rewrite the laws of physics. The particle in question, the muon, a heavier, unstable cousin of the electron that behaves like a microscopic magnet when placed in a magnetic field. According to the standard model, our best theory of particle physics, muons should wobble, or precess, at a very precise rate as they spin. But in April 2021, Fermilab's muon G2 experiment dropped a bombshell. Muons wobble slightly faster than the rules say they should. The discrepancy is minuscule, just 2.5 parts in a billion, but in the hyper-precise world of quantum mechanics, that's like finding a watch ticking a fraction of a second too fast and realizing it might be powered by an unknown force. The anomaly stems from quantum foam, the seething soup of virtual particles that constantly pop in and out of existence around muons. These fleeting particles subtly alter the muon's magnetic properties, and the Standard Model painstakingly accounts for every known contributor from photons to quarks. But Fermilab's results suggest something's missing, an extra ingredient in the quantum soup, perhaps a new particle or force that's evaded detection so far. The most tantalizing possibility, a hint of supersymmetry, a theory proposing every known particle has a heavier superpartner. These shadowy particles could be whispering to muons, tweaking their wobble in ways the Standard Model doesn't predict. Alternatively, the anomaly might point to hidden dimensions or dark photons, carriers of a secret force mediating between our world and dark matter. But before we rewrite the textbooks, there's a catch. At the same time Fermilab was gathering data, a rival approach, Lattice QCD, which simulates quark interactions on supercomputers, produced a revised Standard Model prediction that aligned closer with the experimental results. Suddenly, the gulf between theory and observation narrowed, leaving physicists in a tug of war over whose calculations to trust. That's why the stakes are so high. If Fermilab's anomaly holds, it could be the first crack in the Standard Model's decades-long reign, a glimpse of physics beyond our current understanding. If not, it'll join the long list of tantalizing near misses that pushed science to the brink of revelation, only to slip back into the shadows. With more data pouring in from Fermilab's ongoing runs, the next few years could settle the debate, proving whether we're seeing the first flicker of a new cosmic rulebook or just the universe's latest sleight of hand. When we talk about the Big Bang, we often picture an explosion of energy birthing the first atoms, hydrogen, helium, and a trace of lithium. These elements should have been forged in precise amounts during the universe's first 20 minutes, a process called Big Bang nucleosynthesis. The calculations are elegant. Based on the density of protons and neutrons in the early cosmos, we can predict exactly how much of each element should exist today. And for the most part, the numbers match reality, except when it comes to lithium. According to the theory, the Big Bang should have produced about 3 times more lithium-7 than we actually observe in the oldest stars. This mismatch isn't just a rounding error. It's a glaring inconsistency in our origin story, known as the lithium problem. Think of it like baking a cake with a recipe that's been tested 1,000 times, only to find a key ingredient mysteriously missing every single time. One explanation points the finger at stars themselves. Ancient stars, known as population Roman II stars, act as cosmic time capsules, preserving the pristine chemistry of the early universe. But what if they've been secretly destroying lithium over billions of years? Some models suggest these stars might drag lithium into their fiery cores, where extreme heat fuses it into heavier elements, effectively erasing the original traces. Others propose that lithium could be mixed into deeper layers of these stars, hidden from our telescopes. Yet when astronomers compare stars of different ages and compositions, the lithium deficit remains stubbornly consistent, as if something scrubbed it from the cosmos long before these stars even formed. Then there's the more radical solution, primordial black holes. These hypothetical relics, some no heavier than a paperclip, could have formed in the chaotic instants after the Big Bang. If they existed in vast numbers, they might have gobbled up lithium-rich pockets of the early universe like cosmic vacuum cleaners. But here's the catch: we've never directly detected a primordial black hole. Their existence hinges on their ability to explain not just the lithium problem, but other puzzles like dark matter. A third possibility rewrites the physics of the early universe altogether. What if nuclear reactions in those first minutes didn't play out exactly as we've modeled? Subtle tweaks to the strength of fundamental forces or the presence of unknown particles could have altered lithium production. Some theorists even speculate that certain forms of dark matter could have interacted with protons and neutrons, throwing off the delicate balance of nucleosynthesis. The stakes are higher than they seem. Solving the lithium problem isn't just about fixing a spreadsheet, it's about testing whether we truly understand the universe's first moments. If primordial black holes or dark matter are the culprits, their fingerprints could be hiding in other cosmological anomalies. And if stars are the lithium destroyers, we'll need to rethink how these ancient furnaces evolve. For now, the lithium problem remains an open wound in our cosmic timeline, a quiet reminder that even the clearest predictions can clash with reality. Whether the answer lies in hidden physics, elusive black holes, or stellar sleight of hand, one thing's certain: the universe's first recipe is missing an ingredient, and we're still searching for the cook. Deep beneath the Gran Sasso mountain in Italy, shielded from cosmic rays by 1,400 meters of solid rock, a peculiar detector has been picking up a signal that defies easy explanation. The Dama/Libra experiment, a vat of ultra-pure sodium iodide crystals, has recorded the same strange pulse every year for over 2 decades, a rhythmic surge in flashes of light that peaks every June and dips every December like clockwork. The researchers behind it claim this is the long-sought signature of dark matter, the invisible glue holding galaxies together. But if they're right, why does every other dark matter hunt on Earth come up empty? The theory behind Dama signal is elegant in its simplicity. If our solar system is drifting through a vast halo of dark matter particles, Earth's orbit around the Sun should create an annual modulation. Picture running through a snowstorm. The flakes hit your face faster when you move into the wind, slower when you move with it. Similarly, as Earth orbits, it should plow more heavily into dark matter particles in June when its motion adds to the Sun's movement through the galaxy, and less in December when it moves away. Dama crystals, designed to light up when particles collide with their atomic nuclei, seem to catch this seasonal ebb and flow. Yet from the moment the first results dropped in the 1990s, skepticism flared. The biggest red flag: no other experiment, from xenon liquid argon vats to LUX's ultra-sensitive detectors, has seen anything resembling Dama signal. These rival projects boast far greater sensitivity to the most popular dark matter candidates, weakly interacting massive particles, or WIMP. If Dama's seeing WIMP, why are they invisible everywhere else? Some critics argue the signal could stem from mundane sources like seasonal temperature shifts or fluctuations in cosmic ray backgrounds, though the Dama team insists their shielding and controls rule this out. Then there's the sodium iodide itself. Unlike detectors using xenon or germanium, Dama crystals might interact with dark matter in unique ways. Some theories suggest dark matter could couple more strongly to sodium or iodine nuclei, making it visible to Dama but silent elsewhere. Another tantalizing, if controversial, idea is that Dama's spotting a different kind of dark matter entirely: lightweight particles called axions, or even charged dark matter that interacts electromagnetically. The plot thickened in 2020 when the Anomalies experiment, also using sodium iodide, reported 3 years of data that neither confirmed nor fully refuted Dama. Their modulation was statistically weaker, leaving the door ajar for both error and discovery. Meanwhile, the cosine 100 detector, another sodium iodide rival, saw no modulation at all, deepening the mystery. What makes this debate so electrifying isn't just the science, it's the human drama. The Dama team, led by physicist Rita Bernabe, has held firm for decades, weathering criticism with meticulous rechecks of their data. Their persistence has forced the physics community to confront uncomfortable questions. Are we missing a subtle dark matter interaction? Could multiple forms of dark matter exist, some visible only under rare conditions? Or is there an overlooked systematic error, a ghost in the machine mimicking a cosmic signal? Upcoming experiments like Sabre and Cosine 200 aim to settle the score with even purer crystals and better noise rejection. But until then, Dama pulse remains a haunting enigma, a flicker in the dark that could be the whisper of an invisible universe or the echo of something far more ordinary. Either way, it's a reminder that science's most stubborn anomalies often lead to its greatest leaps. At the heart of our galaxy, where supermassive black holes lurk and stars swarm in their billions, NASA's Fermi Gamma-Ray Space Telescope has spotted something that shouldn't be there, an eerie, diffuse glow of gamma rays radiating from the Milky Way's core. This galactic center excess defies simple explanation, flickering with energy equivalent to thousands of suns yet spread across hundreds of light years. The puzzle: we can't tell if it's coming from a celestial demolition derby of dead stars or something far more exotic, the annihilation of dark matter itself. Let's start with the pulsar scenario. The galactic center is a graveyard of stellar remnants, with spinning neutron stars called millisecond pulsars peppering the region like cosmic lighthouses. These ultra-dense corpses emit beams of gamma rays as they rotate, and with enough of them clustered together, their combined glow could theoretically explain the excess. Supporting this, Fermi's data reveals faint point sources, pinpricks of gamma rays that might be individual pulsars hiding in the noise. The catch: there should be far more of these point sources than we've found. Current models suggest it would take roughly 10,000 pulsars to account for the glow, yet follow-up observations with radio telescopes have only confirmed a fraction of that number. It's like hearing a roar in a forest and only spotting a handful of crickets. Something's not adding up. That's where dark matter steps in, or rather, crashes together. If dark matter consists of weakly interacting massive particles, WIMP, their collisions near the galaxy's core could produce gamma rays as a byproduct. Picture two ghosts colliding in the night, their impact sparking a flash of light in a realm we can't see. The Milky Way's center, with its dense dark matter halo, would be the perfect arena for such annihilation events. Intriguingly, the gamma-ray excess follows an energy distribution that matches some WIMP models almost perfectly, a tantalizing hint that we might be glimpsing the invisible universe's shadowy fireworks. But here's where the plot thickens. The excess isn't perfectly smooth. It shows subtle clumps that could either be unresolved pulsars or fluctuations in dark matter's distribution. To settle the debate, scientists have turned to a clever proxy: dwarf galaxies. These tiny satellites of the Milky Way are rich in dark matter, but lack the stellar hustle and bustle of the galactic center. If gamma rays from dark matter annihilation are real, dwarf galaxies should show them too, just fainter. Fermi has scrutinized these dwarfs for over a decade, and while a few show tentative gamma ray hints, none match the galactic center's intensity. It's a puzzling contradiction. Either dark matter behaves differently in different environments, or we're missing a crucial piece of the astrophysics puzzle. Now enter the wild card: asymmetric dark matter. Most models assume dark matter particles are their own antiparticles, meaning they annihilate on contact. But what if they're not? Alternative theories propose two distinct dark matter species, particles and antiparticles, that could decay rather than annihilate, producing gamma rays along the way. This could explain both the excess and the dwarf's silence, as decay signals would be fainter in less dense regions. Others suggest action-like particles, which could convert to gamma rays in the galaxy's magnetic fields, adding another layer of complexity to the hunt. The quest to crack this enigma is accelerating. Next-generation telescopes like the Cherenkov Telescope Array will scan the galactic center with unprecedented resolution, hunting for the telltale flicker of individual pulsars. Meanwhile, particle colliders and underground detectors continue their silent vigil, searching for dark matter's fingerprints in realms beyond light. Whatever the answer, pulsars, WIMP, or something entirely unexpected, the galactic center excess stands as a beacon in the dark, reminding us that the universe's greatest puzzles often shine brightest where the night is deepest. The Eridanus supervoid isn't just an empty patch of space, it's a staggering cosmic absence, a bubble of near-nothingness stretching over 1 billion light-years wide. Nestled in the constellation Eridanus, this void is so vast it could swallow thousands of galaxies whole, yet it contains almost nothing, just a sparse scattering of stars and gas, like a single grain of sand lost in a desert. But here's what makes it truly extraordinary. It lines up almost perfectly with the CMB cold spot, that enigmatic chill in the cosmic microwave background that defies conventional explanation. Could this void be casting a shadow across the fabric of the universe, or is their alignment something stranger, a clue to forces we don't yet understand? On paper, the connection seems straightforward. The integrated Sachs-Wolf effect predicts that light traveling through voids should lose energy as it climbs out of their shallow gravitational wells, cooling the CMB in those regions. Picture rolling a ball uphill. It slows down, losing kinetic energy. For photons, that energy loss translates to a slight redshift, leaving a cold imprint on the microwave sky. The Eridanus supervoid, with its yawning emptiness, should be the perfect culprit for the cold spot's deep freeze. But there's a problem. This void isn't nearly as empty or as large as it needs to be to explain the temperature dip we observe. Simulations suggest a void would need to be twice as vast and far more devoid of matter to match the cold spot's intensity. It's like trying to explain a freezer's chill with the breeze from an open window. The scale just doesn't add up. That's where things get speculative. Some theorists propose the void might be part of a larger underdensity, a nested hierarchy of emptiness that amplifies the effect beyond what we've mapped. Others wonder if dark energy's repulsive force is acting more strongly inside the void, stretching it faster than the surrounding universe and deepening its gravitational imprint. Then there's the radical idea that the Eridanus supervoid isn't just a hole in space, it's a scar. In certain multiverse models, collisions between bubble universes could leave behind vast, empty regions where spacetime itself was wounded, creating voids that carry echoes of a larger cosmic structure beyond our own. But perhaps the most tantalizing clue lies in the void's galaxies, or rather, their strange distribution. Surveys like the Dark Energy Survey have found that the galaxies within the Eridanus supervoid aren't just scarce, they're oddly clustered, as if drawn toward invisible strings. This peculiar arrangement has led some to suggest the void might be laced with dark matter filaments, unseen tendrils that warp the motion of stars and gas in ways we can't yet model. If true, it would mean the void isn't truly empty, just filled with something we can't see, a hidden architecture shaping the nothingness. The hunt for answers is pushing telescopes to their limits. Upcoming missions like the Vera Rubin Observatory's Legacy Survey of Space and Time will map the void's structure in unprecedented detail, while next-generation CMB experiments like CMB-S4 will scrutinize the cold spot's polarization patterns for hints of exotic physics. What they find could rewrite our understanding of cosmic evolution or force us to confront an even stranger possibility, that the cold spot and its void aren't just anomalies, but windows into a universe far more complex and interconnected than we ever imagined. Because sometimes the most profound mysteries aren't found in the light, but in the shadows cast by what's missing. For all the stars, galaxies, and planets we've mapped across the cosmos, there's a glaring hole in our accounting of the universe's contents. Scientists call it the missing baryon problem, a cosmic detective story where roughly half the normal matter predicted to exist has seemingly vanished without a trace. Baryons are the particles that make up everything we can see: protons, neutrons, and the atoms they form. And according to the Big Bang's recipe, they should account for about 5% of the universe's total mass energy. Yet when we tally up all the visible matter in stars, gas, and dust, we come up shockingly short. So where is it hiding? The answer might lie in the most elusive cosmic architecture of all, a ghostly web of superheated gas threading between galaxies, known as the warm-hot intergalactic medium, or WIMP. Imagine the universe as a vast metropolis with galaxies as glittering skyscrapers connected by an intricate subway system. Only in this case, the subway tunnels are filaments of ionized gas, scorching to temperatures between 10,000 and 10 million degrees, stretching for millions of light years. This is the WIMP, a diffuse, electrified fog so thin it's nearly transparent, yet so expansive it could house the bulk of the universe's missing atoms. The challenge: gas this hot doesn't emit visible light. It's like trying to spot steam rising from a kettle in a pitch-black room. But there's a workaround. When distant quasars, the brilliant cores of active galaxies, shine their light through these filaments, the WIMP leaves faint absorption lines in their spectra, like fingerprints in ultraviolet and X-ray wavelengths. The real breakthrough came with X-ray telescopes like ESA's Newton and NASA Chandra. By staring at distant quasars for hundreds of hours, astronomers spotted telltale dips in their X-ray light, signatures of highly ionized oxygen atoms embedded in the WIMP. These observations suggest the filaments aren't just theoretical, they're real, tangible structures weaving through the cosmic web like invisible highways. But here's the catch: even with these detections, we've only accounted for a fraction of the missing baryons. The WIMP gas is so tenuous that its total mass depends on extrapolating sparse data points across unimaginable voids, like weighing an ocean by sampling a few drops. Part of the problem is temperature. The WIMP isn't uniformly hot. It ranges from lukewarm to blistering, with different zones absorbing different wavelengths. Some filaments might be too cool to show up in X-rays but too warm to appear in ultraviolet, slipping through our observational nets entirely. Others could be tangled in knots of dark matter, their gas too scattered to detect with current instruments. Then there's the complicating factor of cosmic variance. The WIMP density fluctuates wildly across space, meaning our local observations might not reflect its true average abundance. It's like trying to measure Earth's ocean levels by sampling only a handful of lakes. Some might be deep, others nearly dry with no clear pattern. The hunt is now shifting to next-generation tools. The upcoming Athena X-ray Observatory, set to launch in the 2030s, promises to map the WIMP in unprecedented detail, while radio telescopes like the Square Kilometre Array will probe its cooler phases using hydrogen emissions. Even more tantalizing are the indirect methods, like studying the distortions the WIMP imposes on the cosmic microwave background, subtle warps in spacetime that could reveal where these filaments pile up. What makes this search so thrilling isn't just the prospect of balancing the universe's ledger. It's the realization that the cosmos's empty spaces are anything but. The WIMP represents the last great reservoir of ordinary matter, a shadowy infrastructure tying galaxies together in a network we're only beginning to trace. And as we peel back its layers, we might find more than just missing atoms. We could uncover the hidden rules governing how the universe distributes its wealth, one invisible thread at a time. What if the universe isn't what it seems, not a physical expanse, but an unfathomably complex simulation, its reality rendered in invisible code? The simulation hypothesis, once relegated to science fiction, has crept into serious scientific discourse, fueled by eerie parallels between quantum mechanics and the glitches you might expect in a virtual world. Take Planck-scale physics, for instance. At distances shorter than 1.6 times 10 to the power of -35 meters, the so-called Planck length, space itself becomes grainy, like a digital image zoomed in too far. This fundamental limit isn't arbitrary. It's the resolution at which spacetime stops being smooth and starts behaving like a pixelated grid. Could this be the universe's built-in render distance, a processing constraint to prevent the cosmic computer from overloading? Then there's quantum indeterminacy, the bizarre fact that particles don't have definite properties until measured. It's as if the cosmos conserves processing power by only calculating the spin or position of an electron when someone's looking, a cosmic version of video game optimization where distant objects lack detail until a player approaches. Even the infamous double-slit experiment, where particles act as waves when unobserved but snap into particles under scrutiny, echoes how a simulation might reduce computational load by simplifying unobserved systems. The universe's refusal to pin down reality until the last possible moment feels less like a fundamental truth and more like a clever shortcut in some cosmic code. But the most tantalizing hints come from mathematical fine-tuning. The laws of physics rely on constants so precisely calibrated that altering them by a hair would collapse stars, unravel atoms, or prevent life altogether. The strength of gravity, the mass of an electron, these aren't just numbers, they're parameters dialed in with impossible precision. To simulation theorists, this isn't luck, it's evidence of deliberate design, a programmer tweaking variables until the simulation runs smoothly. Even the universe's love for fractals and repeating patterns, from spiral galaxies to the branching of trees, mirrors how simulated worlds reuse algorithms to save memory, like a game recycling textures across different landscapes. Skeptics, of course, have counter-arguments. The Planck length might simply mark where gravity and quantum mechanics clash, not proof of digital architecture. Quantum weirdness could reflect deeper layers of reality we don't yet grasp, not processing limits. And the fine-tuning problem might find answers in the multiverse, countless universes with random constants, ours just the one where life could notice them. Yet the simulation hypothesis persists, buoyed by a chilling thought. If civilizations far older than ours exist, their computing power would dwarf ours to godlike degrees. Creating ancestor simulations, virtual worlds indistinguishable from reality, might be trivial for them. Statistically, we're more likely to be one of those simulations than the original universe. Whether cosmic coincidence or cosmic code, the simulation hypothesis forces us to confront a profound question. If reality is programmable, what else might be possible? Glitches in the matrix like déjà vu or quantum tunneling could be bugs in the system. The speed of light, a firewall preventing processing overload. And if the simulators exist, do they watch us, study us, or are we just background noise in an infinite stack of simulations within simulations? The answer might lie in experiments to uncover jagged edges in reality, like anomalies in high-energy particle collisions or asymmetries in the cosmic microwave background. Until then, we're left with a universe that behaves suspiciously like a masterpiece of engineering, whether by nature's hand or a coder's keystrokes. From dark energy's relentless push to the quantum whispers of entangled particles, these 30 unseen forces don't just shape the universe, they rewrite what we thought was possible. They tear up the cosmic rulebook, revealing a reality far stranger and more interconnected than we ever imagined. Whether it's the phantom tug of the Great Attractor or the ghostly wobble of muons defying physics, each mystery peels back another layer, showing us how much we've yet to learn. Some of these enigmas might crack open in our lifetime. Imagine waking up to headlines that dark matter has been caught in a lab or that Oumuamua's secrets are finally decoded. Others, like the true nature of consciousness or whether we're living in a simulation, could linger for centuries, taunting us with their elusiveness. But that's the thrill of exploration. Every answer births new questions, and every discovery reveals deeper layers of the unknown. So here's the real question for you: which of these forces keeps you up at night? Is it the cosmic horror of black hole firewalls or the elegant cruelty of the lithium problem? Maybe it's the eerie silence where alien signals should be, or the way quantum particles communicate faster than light. Drop your pick in the comments, and while you're there, hit subscribe. Because the universe isn't done surprising us, and neither are we. The next deep dive is always just one click away, and who knows, the next breakthrough might be the one that changes everything.